Post-stroke rehabilitation through walking steps tolerance study, using VPT research method, number 1451, VPT Sharp 017, November 28, 2025. Gerald C. EclaireMD Foundation. Category, Exercise Medicine. Preface. For 43 years, I studied mathematics, physics, computer science, AI, engineering, and medicine. My research always followed one core belief: all systems on Earth follow the same math rules and physics laws, even if humans express emotions and passion on top. This study applies that belief to exercise medicine after my hemorrhagic stroke on June 21, 2025. A stroke is a boundary-changing, irreversible event. After my stroke, I reduced my daily walking from 15,000 steps to about 7,000 to 8,000 steps per day. This was not weakness. It was a health decision to protect injured brain vessels and save energy for my brain to adapt and heal. Introduction. Exercise medicine is not just about muscles, bones, or joints. It is also about how much our blood flow, metabolism, brain, heart, and organs can safely handle when we exercise. Walking steps are a personal measure of my daily exercise dose. Step counts give a simple and clear number that shows how much walking the body can tolerate each day. While working under long-term internal stress, a healthy body normally resets itself every day after exercise. But real internal stress to blood vessels and organs does not fully reset overnight. The effects add up over months and years. This makes step tolerance a useful number to track for long-term health study. Why walking steps can be used as strain. Step numbers show the highest safe daily walking limit the body can tolerate. Stress inside the body accumulates like pressure and load on a pipe in engineering. After my stroke, my safe walking ceiling became lower and stabilized around 7K to 8K steps daily. This study focuses on how stress narrows tolerance limits, not on whether more steps trend up or down. Using steps as the strain axis helps compare long-term stress burden clearly. Physiological meaning of 4 stress inputs. This study uses 4 stress inputs. These affect step tolerance over time. Each stress has very different biological meaning, even if some numbers may seem similar on a daily chart. 1. SBP, systolic blood pressure. SBP is the highest pressure reached when the heart pushes blood out. It acts like repeated short strong pushes on artery walls. Repeated high SBP over time can make artery walls thicker and weaken small branches in the brain, retina, and kidneys. After stroke, I use 115 mm of mercury as my safe normalization value for SBP to reduce future stroke risk. 2. PP, pulse pressure. PP is how much arterial pressure rises and falls with each heartbeat. In stiff or older arteries, these swings hit fast and strong like repeated knocks. Over many years, this can cause micro cracks in the vessel inner layer, faster calcium buildup, calcification, narrowing of tiny vessels, micro bleed risk in the brain, retina, and kidneys. My recent PP data centers around from 44 to 49 mm of mercury. This is why 45 mm of mercury is a realistic normalization value to measure pulsatile stress, PP. 3. MAP, mean arterial pressure. MAP is the average pressure load the heart must pump against at all times. It is like constant water pressure in a pipe. When MAP stays high for too long, it causes heart muscle thickening and shape change over time. Kidney filter stress, less oxygen and nutrients reaching tissues, tired cells and lower body energy, less rest oxygen for the brain, lower exercise tolerance ceiling, smaller safe daily step dose. Because MAP acts nonstop, it becomes the biggest long-term stress burden, even if daily numbers seem normal. After my stroke, my safe step ceiling is mainly decided by MAP. I use 85 mm of mercury as my acceptable MAP tolerance boundary. 4. FPG, fasting plasma glucose. FPG measures blood glucose at its lowest digestion point, fasting. When FPG stays high over many years, it causes silent stress on microvessel inner walls, organs that need steady oxygen and nutrients, body energy needed for brain repair, healing adaptation capacity. I use 90 mg/dl as my safe normalization or tolerance anchor for fasting glucose. VMT analysis results. Timeframe selection. I studied 7 monthly time blocks from May 2025 to November 2025. May is used as the starting point and initial condition before the stroke. June is my stroke month, June 21, 2025. July to November are my post-stroke months. Key observations. First, the correlation results between the 4 stress inputs and the strain output fall between 29% and 43%, which is low and not meaningful. This shows that traditional statistics method only show the surface, not the insights of real stress load building up inside the body. Second, the VMT energy shows how 4 pressure and glucose stresses shared long-term burden on the body. FPG is 24.4%, SBP is 25.2%, PP is 25.3%. MAP is 25.2%. Why MAP may still look like the highest, even when percent values are nearly the same. FPG, SBP, and PP go up and down every day. Because of eating, movement, sleep, and emotions, their stress time is broken into short daily cycles. MAP acts differently. It stays in a narrow band of from 83 to 89 millimeters of mercury. It presses on circulation and organs all the time, even when the body is resting. Because MAP is constant, not paused or reversed each day, its stress influence grows steadily on the heart, brain, and kidneys. When a system is measured by total accumulated stress energy, a constant pressure always shapes the tolerance boundary, more than stresses that rise and fall daily. That is why MAP often dominates strain tolerance, even if its percent looks similar to others in a short timeline summary. In short, MAP carries a non-stop load, so it affects exercise tolerance limits more strongly than fast-changing stresses that reset partly each day. Third, the stress energy climb month by month looks like this: cumulative VMT energy percentages: May 0%, June 51%, July 83%, August 82%, September 96%, October 99%, November 100%. What this means in simple words: the two big jumps in June, 51%, and July, 83%, shows a major shock to the system. My stroke happened near the end of June. After July, stress energy stayed very high every month, above 82%, because the body does not reset like a machine. By November, the system reached its 199% level, the highest recorded stress shaping effect for this 7-month period. Conclusion for everyday readers: traditional statistics focus on averages, and can miss real stress burden inside one person's body. In your case, correlation values were low, but VMT energy showed a real and meaningful stress load when measured by total accumulated burden. Topological data analysis and viscoplastic energy both support studying stress impact by shape and accumulated energy, not by averages alone. MAP is a steady pressure load that never pauses. It affects blood flow that carries oxygen and nutrients to organs like the brain, heart, and kidneys. Because it runs 24 hours a day, its influence on long-term organ stress becomes very strong, even when daily numbers stay in a safer band. Walking steps clearly show daily exercise tolerance. Your safe ceiling dropped right after the stroke month, then recovered and stabilized at a new safe limit. The drop from 10K steps in May to 3K in July, right after stroke, happened because total internal stress narrowed the safe exercise limit, not because walking is harmful. Living biological systems do not reset fully after major injury. Stress history remains and continues to shape the body's tolerance boundaries over time. TDA analysis results. TDA, topological data analysis, studies how data points connect and how their geometric shape changes over time. It does not focus on averages alone, but on how the system behaves as one whole, especially when the system carries stress that keeps reshaping its boundaries and tolerance limits. This analysis studies the geometric shape of my post-stroke recovery data using 3 main signals: walking step tolerance, K steps, pulse pressure swings, ppn3, constant organ pressure load, affecting oxygen and nutrients delivered by blood flow, MEP4. The word tolerance is important. Here, walking steps show my daily exercise dose that my body could safely tolerate during each month after the stroke shock. When I walk, my heart must pump harder, and my organs must receive enough oxygen and nutrients to support body movements. The maximum number of walking K steps I can safely manage is not random. It is shaped over time by my internal stress load, coming from blood pressure and glucose responses. To make fair geometric shape comparisons, each month reading was normalized, using stable healthy reference anchors used in longevity and internal medicine studies: 90 mg/dl for FPG, 115 mm of mercury for SBP, 45 mm of mercury for PP, and 85 mm of mercury for MAP. Normalization means converting each pressure stress reading into a healthy risk ratio by dividing its value by the best known healthy level, so numbers can be compared fairly across months. In most biological risk tracking, using stable reference anchors gives TDA a fair space for geometric shape and data points distance and connectivity comparison. Even when one injury event changes the boundary, the 3D scatter plot placed 5 months, July 2025 through November 2025, as points inside a visual tolerance space shaped by my stress strain history. The 3D space has 3 axes: x-axis, walking K steps, tolerance boundary; y-axis, ppn3, pulse pressure swing stress; z-axis, MEP4, steady perfusion pressure stress. This 3D view has a clear story. July sits far from all other months, in the lowest walking tolerance zone. This matches the post-stroke shock condition, where my body could safely manage only about 3K steps per day right after the stroke. That point is not just lower in trend direction, It is geometrically distant, meaning the system boundary was very narrow, under extreme internal stress strain energy. It marks the steepest tolerance loss compared to months that follow. After July, the points move upward in one smooth, connected cluster line across space, showing recovery. August sits at 5.3 k steps, September at 7.1 k steps, October, near 7.8 k, and November at 8.2 k steps. This upward curve is continuous, forming one connected path without breaks or isolated groups. This means the tolerance range regained capacity month by month through biological adaptation, not daily reset or erratic behavior. TDA also checks if my blood pressure stresses worsened sharply, created isolated clusters, or spiked unpredictably. The stresses ppn3 and MEP4 both stayed in one narrow, compact, background region in the plot. Even though their values moved slightly between months, there were no sharp spikes or space-isolated points. These recovery patterns can be clearly seen in the 3D scatter and radar chart. This confirms that stress energy was controlled in a biologically realistic band, while tolerance boundary, walking steps, recovered outward. The 5-month radar chart added a second shape view. A radar chart turns numbers into a circle shape, where each direction, called a radial axis, shows one signal. In this study, the radar chart plotted these directions: normalized walking tolerance, steps, pulse pressure, ppn3, mean perfusion pressure load, MEP4. The radar chart shape expands outward month by month from July to November 2025, just like a healing boundary surface stretching outward as tolerance returns. July has a very small step radius, then August is wider, September wider again, October, even closer to the outer edge, and November reaches the largest radius. The radar shape confirms geometric expansion of the tolerance limit, not separation, and not fragmentation. The steps did not stall or loop backward, meaning the biological system adapted forward and increased its safe daily walking ceiling gradually. In exercise tolerance studies, the best recovery month is not always the month with the lowest stress numbers. Some people assume lower stress must mean better recovery, but that idea comes from statistical trend thinking based on averages. Biology works differently. The body adapts forward after a major injury, and the best condition is the month that reaches the highest safe tolerance, without stress spikes, such as seen in research at MIT. But here, the 3D scatter and radar shape both show that while September had the lowest PP and MAP stress signals, it did not reach the best total condition. This is because the key question is not whether pressure stress was low. The key question is, what exercise dose could the body handle safely at that moment, while keeping stresses stable? That answer is November 2025, which reached the highest step ceiling tolerated safely without stress spikes. A clinician looking at one patient could use this chart logic. A doctor or researcher may look at a single person and ask, 1. Did exercise tolerance shrink toward a lower ceiling, when stress energy built up silently in the background? 2. Did the system boundary recover gradually without sharp stress worsening? 3. Which stress defined the narrowest tolerance boundary over the long term? In this dataset, MAP carried the largest share of shaping influence in tolerance modeling because it acts non-stop. It shapes the long-term cardio-organ circulation boundary by affecting oxygen and nutrients delivered by blood flow even at rest. PP injures through vibration like stretch, but has slightly smaller boundary shaping burden when measured by accumulated area. FPG moves up and down in short, metabolic windows, influencing small vessels but not dominating the boundary of exercise tolerance in a long-term view. TDA conclusions confirm. Recovery followed one continuous, connected space path. Stress input stayed clustered, stable, and not isolated. MAP carried the strongest steady boundary shaping influence. Walking tolerance adapted forward but did not reset daily. The best tolerated exercise ceiling condition was November 2025. More of this approach echoes boundary-aware shape modeling used in MIT labs from 1970 to 1980, especially models that study system boundaries and shape deformation, not averages alone. When I talked about MIT models, the closest examples are mechanical engineering and EECS AI modeling tools that study boundaries, shape changes, and tolerance limits instead of averages alone. At MIT, many labs build models like stress-strain systems that measure how forces shape a structure over time. Similar to work in MIT mechanical engineering, AI models that recognize patterns from geometry, inspired by Patrick H. Winston, who taught reasoning from data shapes and limits. I took several courses of AI and machine learning from Professor Winston, during from 1973 to 1974 at MIT. Special note regarding autophagy. Yes, I have researched the subject of longevity through autophagy. This post-stroke exercise medicine study is just a small part of that larger effort. My fasting plan is described below, changing from 3 meals a day to 2 meals a day. Brunch and dinner, naturally extends my daily fasting window. A longer fasting period allows my cells to have more continuous, uninterrupted hours to activate autophagy. Autophagy is the body's built-in cell cleaning and repair system, which removes old or damaged cell parts and proteins. Eating one less meal often reduces insulin activity for a longer stretch each day. When insulin is low, autophagy can continue running instead of being paused for digestion. While this supports cellular repair, I must also be cautious about hypoglycemia, which can be dangerous and must be actively monitored. Autophagy was discovered by a Japanese scientist, Yoshinori Ozumi, whose fasting research inspired many longevity studies. His work demonstrated that fasting activates the cell cleaning system. Many scientists studying longevity and intermittent fasting further support a 2-meal daily structure, provided total nutrition remains adequate. A sustainable fasting plan must also include careful attention to food quantity and food quality. When I do eat, my body must still receive enough nutrients, especially non-processed protein and fresh vegetables, so my cells have the necessary materials to rebuild and repair during fasting. In summary, 2 meals a day can naturally lengthen fasting hours every day. Longer fasting hours support more autophagy activity for cellular repair. Monitoring nutrition, portion size, and meal balance keeps it safe and sustainable. I apply the principle of simplicity with purpose. This is a deliberate lifestyle design that supports cellular repair, long-term metabolic health, and longevity. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is for educational reference only and is not medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights for this article belong to the author, Gerald C.